Hi everyone, I am Ananthalakshmi. I am the IIT Madras ETDCS expert faculty. Okay, again, organic chemistry acid-base questions like last time. Okay, so we are given 4 compounds and we have to see which of the following options are correct statements. Let's see the first. The order of basicity is 2 greater than 1 greater than 3 greater than 4. Okay, here we are asked to find order of basicity. So how basic this compound will depend on how easily this n lone pair, the lone pair of n can be donated. Okay, so more easily with which we can donate the lone pair of the amine group, then more basic the compound will be. So that's the whole that is the whole point of the that is the basic concept you have to keep in mind. Okay, now let's see each options. So here you have this lone pair, but then it involves in resonance. And here you have this lone pair, even though it involves in resonance, it has this plus I effect from these 3 groups, which increase the electron density. Electron density. So obviously 2 is much better than 1. Perfect. Okay. Now compare 3 and 4. Great. Okay. So in 3, this thing is same as this, but with NO2 group. But NO2 group is not good because NO2 group has minus I effect, which increases the resonance of this lone pair in this benzene. So it's not, it will be the least basic actually. It will be the least basic. Okay. And okay, this fourth one is something which is a very common concept, but still very important concept. So here we'll discover a concept which is SIR effect. Okay. Steric inhibition of resonance. So see, in all the cases, this N lone pair is involving in conjugation with the benzene ring, right? But in this case, don't be surprised, lone pair cannot involve in resonance with the benzene ring. Why? Because of the steric effect. Why? Because of this large NCH3CH3 group and NO2 group, which is so adjacent to it. This NCH3CH3 goes out of the plane. Okay, it's not in the plane; it goes out of the plane, and hence if the lone pair goes out of the plane, it can't involve in resonance. So basically, no resonance. So when this lone pair doesn't involve in resonance, then it is very much available to donate to an acid, right? So this is the most acidic. Okay. So fourth one is the most acidic compound. So this one is wrong because fourth one is the most, sorry, not acidic, sorry. Basic. Here we're talking about basic. The fourth compound is the most basic compound because it can easily donate the nitrogen lone pair. Yeah. Now the second one, this magnitude of pKb difference between 1 and 2 is more than between 3 and 4, which is absolutely wrong. Because we have already established that third one is the least basic and fourth one is the most basic. So the pKb difference between 3 and 4 is definitely greater. Okay, I'll just write the basic nature order. So which is the most basic? Fourth one. Which is the least basic? Third one. Which is again a better basic? Second one, because you have plus I effect from CH3 group. And then one is, okay, great. This is the basic relation, the order of basic nature for these 4 compounds. So A is wrong, B is wrong. Now resonance effect is more in 3 than in 4. It is correct because in 4 we don't even have resonance effect because the lone pair is out of the plane and it can't involve in resonance. So that is perfectly correct. Now steric effect makes compound 4 more basic than 3. Exactly. Because of the steric effect, it can't involve in conjugation. It comes out of the plane so that this lone pair is more available to the acids because this lone pair is not busy involving in the conjugation, unlike other compounds. This is an amazing concept. I love this topic. Okay. So this is done. Let's move on. Okay, this is, I would say this is kind of a mains level question. I mean, this is the only mains level question I kind of saw, I guess. This is like, proper JEE 7 question only. And this is from the liquid solution chapter in 12th standard. Okay. So liquid A and B form ideal solution for all compositions of A and B at 25 degrees Celsius. Two such solutions with 0.25 and 0.5 mole fractions of A have total vapor pressures as total vapor pressures as 0.3 and 0.4. Okay, so let's write the data down first. So in the first case, the total pressure P total is 0.3, right? Yeah, 0.3. And in the second case, it is 0.4. Okay, great. We have to find the vapor pressure of, okay, we don't know the vapor pressure of A, we don't know the vapor pressure of B. So these two things we don't know, pure vapor pressure. Okay, but we can definitely know, okay, we have given the mole fraction of A in both the cases. So in this case, mole fraction of A for 0.3 will be what? For 0.3, the mole fraction of A will be 0.25, right? So why am I not able to write 0.25? For 0.4, the mole fraction is 0.5. So we can, since only A and B is present in the liquid, in the mixture, we can say chi B, the mole fraction B will be 1 minus 0.25, which is 0.75. 0.75. And 1 minus 0.5 will be 0.5. So basically, we have to find P naught B, means vapor pressure of pure liquid. The vapor pressure only when there exists a liquid B and no liquid A. That is what we have to find. So what is total pressure? Okay, let's say in a container there is A and B. So this total pressure will be obviously contributed by A and B as well. So can we say the total pressure is chi A, mole fraction of A, into P naught A plus mole fraction of B into P naught B? Yes. This is basically Dalton's law of partial pressure only. And this is Rawls' law. So combination of Rawls' law and Dalton's law will get this. This is a very basic equation in that chapter. So we have two equations and two variables P naught A and P naught B. We can actually solve it, P naught A and P naught B. I'll just write the equation and you can find it. So 0.3 is the P total, chi A 0.25. Okay, I can't really write point here. Okay, 0.25 into P naught A, we don't know. Plus P naught 0.75 P naught B. And we have 0.4 into 0.5 P naught A plus P naught B. Okay. So there are two equations and two variables. If we solve, we'll get P naught B. I'm not solving it, you can solve it. It's just a linear equation solving question. Okay, so this was easy. Now let's move on. Okay, this is a very interesting question from the chapter Ionic Equilibrium. Okay. It would be nice if I can explain the whole concept and go to this question, but okay, I'll try to explain it briefly. Okay, we have a weak base, okay, of 0.1 molar weak base. So basically, we have a weak base here, and we are titrating it with an acid. So in dropwise, this acid will be coming. So this is a strong acid which is given HA. Okay, so it's strong acid weak base reaction. Okay, strong acid weak base reaction. Fine. Now, what we have to find? The variation of pH of the solution with the volume of HA is shown in the figure below. What is the pKb of the base? Okay. Okay, so basically you have some amount of base, some volume of base, and some volume of acid. So let's say this weak base, and there is this acid, then we'll get salt. Okay. Sorry, this acid. So into the base, we are actually adding this acid drop by drop. So that is what is given. So we are adding 2 ml, then we are adding next 2 ml, it will become 4 ml, then it becomes 6 ml. So like that. Okay. So we can see for this 0 to 6 region, As we keep on adding the acid, we can see the pH is not changing much. Okay, it's almost kind of constant. And this region is called a buffer region. And there is a good reason as to why it is kind of constant that we'll learn in detail in ionic equilibrium. Okay. Uh, so till 6 ml, it's a buffer region. And exactly at 3 ml, okay, here. And this is 11. Okay. At this point, the concentration of base and the salt will become equal. And that point is called buffer point. And there is a way to find the pKb also. So pKb, POH. POH is pKb plus log salt by base. So that is the equation we use for buffer region. Everything we'll study in detail in ionic equilibrium. Okay. So here we know at that buffer point, the pH is 11. And obviously, if pH is 11, POH will be 14 minus 11, 3, right? This basic concept we know. So if POH is 3, and the main point is that at buffer point, the concentration of salt will be equals to concentration of base, which means log salt by base will be 0. Log 1 is 0. So pKb will be 3. POH will be equal to pKb, that is 3. So that is exactly they are asking. What is the pKb value? So how can you find pKb value? This pKb value will become equal to the POH value when the concentration of base equal to concentration of salt. So we should know that the concentration of base equal to concentration of salt in the midpoint of the buffer region. That midpoint I have found out corresponds to 3 ml and pH equal to 11. So basically taking data from the graph and putting it into equation, you're done. Yeah, but I couldn't cover what exactly this buffer point, why the graph is constant here and what is happening. That will be very clear when once we are done with ionic equilibrium chapter. Okay. Now let's move on. I think this is the last. Oh, finally, we have reached the last question that I chose. This is again from the chapter Ionic Equilibrium, where we are focused on the topic solubility. Okay, solubility. This is again not tricky, just using all the theory we know. Okay, so they have given acidified solution of 0.05, 0.05 molar zinc is saturated with 0.1. Oh God. 0.1 molar H2S. Okay. So what is the minimum molar concentration of H plus required to prevent the precipitation of zinc sulfide? They have given the solubility product of zinc sulfide. So we need to find the concentration of H plus so that we are preventing the precipitation of zinc sulfide. See, when precipitation happens, when um, when the uh, when the ionic product, becomes greater than the solubility product, the product of the concentration becomes greater than the solubility product. That is when precipitation happens. So our maximum borderline is when we are equating this KSP. KSP equals zinc 2 plus concentration into S2 minus concentration. So this is kind of the borderline, and we are given this. KSP is 1 point. Okay, I have to start. So 1.25 into 10 power minus 22, and we are given yes, how many? What is zinc 2 plus concentration, which is 0.05 molar, right? And S2 minus concentration, we don't know, right? Yes. So S2 minus concentration will be 125 by 5. Yeah, 25 into 10 power minus 22. Great. So we found S2 minus concentration. Now what they have given, there is H2S also, which have overall dissociation constant as this. Okay. So what is H2S? H2S is 2H plus plus S2 minus. But here they have given the overall K net. The overall dissociation will be K1, K2, which is 10 power minus 21. And we can write the 10 power minus 21 as H plus the whole square into S2 minus basically the product of concentration of products minus, not minus, by the concentration of reactants, H2S. So what we need is H plus ka concentration, right? So we know H2S. H2S is 0.1 mole is given. S2 minus we found out to be this. So basically, we just need to find H plus square concentration. That is 10 power minus 21 into H2S is 0.1. Okay, 0.1 divided by S2 minus, which is 25 into 10 power minus 22. Great. Which will cancel with this. 1 by 25. Okay, so the concentration H plus is 1 by 5, which is 0.2. Yes, so 0.2 molar is our answer. Yeah, so this is again usual question. We'll be easily able to solve once we cover solubility product topic. Yes, so that's it. I hope I did it properly, and thank you. That's it.